Okay, we're going to continue our lessons in thermodynamics. And the stuff we're looking at today is kind of new stuff for you. We didn't talk about this in honors chem, so really pay attention. So, first things first, you notice the title, they talk about spontaneity. You may know what the term spontaneity is in normal, English language. In chemistry, it's a little different, a little. But notice I put here, AKA thermodynamic favorability. That's how College Board likes to write it. So on the AP exam, this is how you'll see it. Okay, so College Board appreciates this terminology over this, although they may use both depending on the time. Okay, so the term spontaneous just means something happens without help or something just happens naturally. So I'm just going to put occurs without help and in parentheses naturally. It just happens. So here's two different scenarios where we're talking about this. If we leave a hot cup of coffee out on the table, it will spontaneously what energy over the time? Well, it's going to get cooler, so it's going to lose energy, and it loses it to where? It loses it to the environment. Okay, I'll put to the environment. Here's another situation. If you walk by a clean room in your home for the next 2 months and put no energy into cleaning it, it will eventually get what? And most of us will say dirty, but what we really want to think about here is it will get disorganized because you will keep adding clutter and stuff like that. And if you're never cleaning it, that's what happens. Okay, so spontaneous systems in the universe therefore have a tendency to, we said they lose energy, thinking about the coffee cup, and become more disorganized. So the two terms that deal with that are, we've talked about energy, gaining and losing energy before, that's enthalpy. And a new term that we're talking about now is called entropy. And so it says the degree of disorganization achieved is dependent on both the change. I feel like this is really important, so maybe highlight this. Both the change in the number of particles over the course of the reaction and the temperature the reaction is occurring at. Also, these two, again, these are the two things that are driving it. The two factors that drive spontaneity are enthalpy and entropy. So you can decide if something will happen on its own based on what the enthalpy and entropy values are combined. Okay, so we just talked about enthalpy. How would you define it? This should just be the heat of a reaction. Abbreviate RXN. Could be gained or lost. I'll put here gained or lost. That's what enthalpy is. If it's less than zero, meaning it's negative, we know it's exothermic. And if it's greater than zero, meaning it's positive, it's endothermic. Okay. It's important. The reason we wrote units here is because you really have to pay attention because sometimes it's kilojoules and sometimes it's joules, like over here on delta S, and they trick you in some problems because if you're trying to add these together, you couldn't do that. So be careful and really pay attention to units. So I'll just put a star next to that so you remember that. Okay. Well, the word entropy, again, this is a new concept for you guys. It is symbolized by delta S. It indicates disorder. And sometimes in College Board terms, they talk about things being more dispersed. Because if you compare like a solid to a liquid to a gas, what would you say is more disordered? We'd definitely say a gas, right? So the most ordered is a solid, and then the least ordered is a gas. So that's when we talk about entropy, that's what we're talking about. So if we have a negative delta S, that means we have less disorder. So it's becoming ordered if it's negative. So an example of that would be if we're looking at becoming ordered is going something from like a liquid to a solid, right? It's becoming more ordered, just as an example. And then if we have positive disorder would be something like just so more disorganized, or I'm going to just put more disorder. And so that could just be the opposite, right? So we could be going from a solid to a liquid. That's an example of that. And again, pay attention to the units here because now we have joules per moles times K, and that makes a difference. So we need to make sure we pay attention to that. Okay. Again, College Board prefers the term thermodynamic and I'm just going to put it short, thermodynamically favorable as opposed to spontaneous. With respect to the parameters that we'll be discussing in College Board, despite the conventions by representing positive value with an inequality that delta H or delta S divided by delta S is greater than 0, and a negative value inequality is less than 0. Okay, so you need to be able to predict whether a reaction will be spontaneous. And there's two ways to do that. You can do it conceptually and you can do it mathematically. So conceptually, I'm just going to write here this chart. You need to be able to know this chart. Just memorize this chart over here. And I'll talk about why in just a second. But let's talk about if something naturally, what do we say nature likes to do? Nature likes to get disorganized and likes to lose energy. So I'm going to go back up here and go, okay, well, if I'm looking at delta H values, nature likes it, I put a little smiley face, likes it when things are exothermic because they're losing energy, and when they become more disordered. So it likes a positive delta S. So I'll put next to that. So if you have those conditions for a reaction, negative delta H and a positive delta S, you're always going to have a spontaneous reaction. So that's what we're going to put always here. Okay. So what about this one? It gains energy and loses disorder. So this is the actual opposite of that, right? So that one is it's never going to be spontaneous. Now, we have other situations here, again, because you can look at this little chart. And our best situations are it's spontaneous, always spontaneous, you can see here. All right. And let's go through these little box and put the things that the universe likes. So, well, let me move the camera a little bit. So the universe likes it when it's exothermic. They do not like it when we decrease entropy. So I'll put that. They like it when we increase entropy. They do not like it when it's endothermic. Universe likes both of these. Universe does not like endo, and decrease entropy it does not like. So that's why that's not never spontaneous. So that's kind of a way you can think about it. And so this one says if it has one thing going for it but not the other, it will sometimes. So this is where it gets tricky. At which point it will depend on the temperature. So kind of circle that so you'll know what's happening. And they'll have to tell you because as you notice, we have low temperatures and high temperatures, and we have different things here. Okay, so let's take a look at just specifically entropy, and then we'll go back to dealing with the temperature when we look at Gibbs free energy. So if we're going from a solid to a liquid, aqueous to a gas, are we getting more disordered or less disordered? We're definitely getting more disordered, right? Because the particles are far apart. So that's an increase in entropy. Therefore, increases in temperature are always accompanied because if we increase the temperature, this occurs, it creates an increase in entropy. And if we would say an increase in delta S, that means it's a positive delta S value. That's how we indicate that it's increased entropy. The other thing we can look at is dealing with the number of particles. So let me give you an example. Let's say that I gave you 20 books to organize on a shelf, and I asked you to organize it. You could organize the books in a certain way. But what if I gave you 200 books and I asked you to organize them? Which one would definitely be have more possibilities of being organized differently? Obviously, the ones that were those 200, right? And so the more possibilities, the more particles, the more possible arrangements, the increased entropy. So the more possible arrangements you could have increased entropy. And then when we look at this, they like to talk about this sometimes in the AP exam. A perfect crystal has at 0 Kelvin has an entropy value of 0 because all particles are in a fixed position. When it's 0 Kelvin, there's no movement. Okay, so just right next to that, all particles are in a fixed position. The other thing I want to mention is the bigger the molecules, so like the higher the molecular weight, the bigger something is. So higher molecular weight and bigger molecules, like just in general, which typically is associated with higher molecular weight, but it may just have more particles, is also associated with a positive delta S value or more disorder. Okay. Now, you can also be able to calculate mathematically. So this was a conceptual way to figure out entropy and talk about entropy. But now let's look at the mathematical way. So you can actually look up values for individual substances. I'm just going to put online because we don't really have page number for that. And I'm going to cross this out because we're not going to do that. So you can actually look up delta S values, and it's very similar to looking at the enthalpy stuff where you're going to multiply by the moles, the coefficients, and when you look up the values, it's going to be products minus reactants in this case. Okay, so let's start looking at some of these problems. Let me move this so you guys can see it. Okay. All right, so let's look at the problems down here in the bottom. Sorry, I'm just trying to make it so you guys can really see it in there. Okay. Oh my gosh. Okay. All right, so let's predict the delta S sign for each of these. So we have a solid and a gas and going to a solid. So if there was a solid involved, that's probably a little more disordered, right, than this side. So this is getting more ordered. So if this is getting more ordered, this is a negative delta S is what that should be. That's how you look at this. Okay, here we have these are both gases. So 4 moles of gas versus 2 moles of gas. Well, this is going to have less particles. So less particles is going to be more ordered or more disordered? So because there's less moles of gas, this is definitely going to be more ordered. So that's going to be negative delta S as well. Let's look at this one. So we had a solid, and now it's been dissolved in water, and it's becoming aqueous. So is that becoming more ordered or more disordered? Well, if this thing's breaking apart and forming aqueous thing, this is definitely more disordered. Okay. And then here we just have a straight solid going to a liquid. This is definitely getting more disordered. So this is definitely a positive delta S as well. So we can predict them like that just by looking at the phases, and they may have you do that in the AP exam. And they also may just have you calculate it. So you'll be given values. You want to memorize them. And I actually wrote them here because I looked them up when I paused it. And we can use these values to actually do some calculations here. Just making sure I wrote this one down right. Yeah, it's 256. It's just hard to read that. 6. Okay. All right. So I think we're just going to calculate it for B. Let's make prediction. Let's just do B for the time without even, let's predict it first, and then let's actually calculate it. So if we look at this, we have 2 moles of gas, and it's going to 3 moles of gas. So this should definitely be getting more disordered. This is a positive delta S. But let's see if that's what we get when we actually calculate it. So again, if we look back up at the formula, it says products minus reactants. So we're going to do the O2, which is 205. It's a product. Okay, plus 2 times the other product, which is the SO2, 248.5. Okay, minus, so all that, minus the reactant, which is the SO3, and we have 2 of them. So 2 times 256.2. And I like to write out what I get separately on the things again. So this is 702, and this I got negative 512.4. And then I ended up getting 189.6, and that's joules per Kelvin. So did that, sorry about the bell. Okay, does that match what we predicted? We predicted a positive delta S, and it's also positive. All right, so perfect. So we only have one more thing left to do, and I think I'm going to have to put it in a separate video, but it's Gibbs free energy. So get ready.